All right, it's 40 after. So this week we're diving into oscillations. It's a new topic for us. But in the beginning, I'll let you guys give me a couple quick questions. If anybody has questions about Thursday's midterm, I sent an email about, and we talked about it in class last week, but also I sent an email about what's covered and what's not covered and what the rules are. You can bring you get your formula sheet, you can use both sides of it. Anyway, that's the only real change from last time. No calculators. But anyway, any questions about the exam? Yeah? No? All right. Cool. I'll do a Q&A also next on Thursday's lecture about the exam, as well as probably more oscillation stuff. Much to cover in this class. All right. So today we're talking about chapter chapter 13, the oscillations, right? And so today, today oscillations. And so it turns out that when physicists look around the world, as they do, right, we look around, what we see is a whole bunch of masses on springs. Everything can be thought of, at least to a first approximation, as something that's got some mass, right, sitting on a spring, something that restores it to some equilibrium position. Like right now, you're all sitting in your seats up there. I'm standing here on my legs, right? And except a couple are milling around, but most of us are holding almost still. And if we were perturbed a little bit, if someone were to come up and nudge us, right, like if you get nudged while you're sitting there in your seat, you would oscillate a little bit. You would be pushed away from the equilibrium position, and then because you're in a stable equilibrium position, hopefully if you're sitting comfortably in your chair, you're in stable equilibrium. That means that if you're nudged away from that, there tends to be a restoring force that puts you back where you came from, right? So this is just it's just like it's like a spring. Springs have a linear relationship between displacement and force. Hooke's law, right? So what is Hooke's law? You've seen it already. Hooke's law is just a linear relationship between your displacement and your force. It says that the restoring force, let's talk about it in one dimension. So the x component of the force is just minus, that's the restorative part, that's the part that says you get pushed back from where you came from. K, that's the stiffness of the spring constant, times delta x. We're just going to call it x today. And we're going to remember that when I write x in this context, it's important that the 0 point for this x, what I mean by x equals 0, that better be the equilibrium position for the mass that's sitting on the end of the spring, right, that's giving this force. So there's no mass in this equation, right? This is saying what force the spring exerts on whatever's on the end of it. It might be my hands pushing on the spring, right, or pulling on it, or pushing on it, whatever I'm doing. It might be a mass that's hanging on the spring, whatever it is. That's the force that's exerted on it. Okay, and as we've seen lots of examples of oscillations. So here's a simple example. I love this roller coaster. You know, I bring out every chance I have. Here's another chance. So a ball sitting at the bottom of the roller coaster, just like you sitting on your seat. If you perturb this thing away from its equilibrium position, it tends to go back where it came from, and what do you know? You get an oscillation. Now, because there's dissipation in this system, because there's friction, right? It doesn't oscillate forever. This is actually a damped oscillator. So I'll talk about that stuff in the lecture a little bit, damped and driven oscillators. But in this class, we're not going to focus too much on damped and driven oscillators. We're going to focus mostly on simple harmonic motion, simple harmonic oscillators that are oscillating back and forth and maintaining their amplitude. I'll define amplitude in a few minutes as well. But this is just what I mean by stable equilibrium position. If you push it away from where it is, whether you push it to the left or the right, it tends to go back where it started from, and it oscillates. So oscillators are everywhere. And this equation, this simple equation for just a Hooke's law spring, a linear spring, I say linear because force is linearly related to displacement, x, with just a proportionality constant in front and a minus sign. That equation will describe all of these cases to first order, right? All right. So now to get into oscillations, the first thing to do is to describe a couple different terms we're going to use. So if you've got an oscillator of any type, even if it's not simple harmonic motion, what do I mean by an oscillator? If you have something that's going through some kind of motion that is repeated. So if I plot something as a function of time, say position, it doesn't have to be position, though. It might be voltage in a wire, or it might be the sound pressure level at your ear, or it could be any number of different things. But plotting as a function of time, if I get some waveform that repeats, that repeats itself. So I'll draw a triangle wave. So here's an example. It's a triangle wave. Right? It's repeating. I'm able to define, no matter what shape this is, if it's repeating, I'm able to define certain aspects of this thing. One is I can talk about the period. So if I take a point on this curve and find the next time where you're in the same place inside the curve, it's, oh yeah, that's the period. We call it capital T. I know capital T also means tension, and it means a bunch of other things. But for the oscillations part of the class, this will be period. That's one thing we can define. Another thing we can define is the frequency. There's going to be several kinds of frequency as we go through oscillations and then go through waves. So right now I'm talking about plain old f for frequency. And by f, I mean the number of cycles, I should say, per unit time that are occurring with this wave pattern, right, with this oscillation. So this thing's oscillating back and forth along this triangle wave. That's a period of capital T. I can define the number of cycles per second as just 1 over t, right? So if it takes, say 5 seconds to get from this point to that point, it means it also takes 5 seconds to get from that point to that point, or from this point right here to that point right there. All these are the same. It doesn't matter that I chose the peak. I just chose it at convenience. But the period is just how long it takes you to get back to the same place again in a repeating pattern. If I then say, well, 1 over t, that's the frequency, it says, well, if t equals 5 seconds, that means the frequency is, what is that, 0.2 hertz? 1 over 5? Yeah, I think that's right. Hertz. What is hertz? Hertz are the units of frequency, ETRTZ, and that's just 1 over seconds. That's all it is. All right? So hertz is just a fancy way to say 1 over seconds. We tend to refer to frequency written as an F here. Right? We talk about that as in hertz. But it's fine if you wanted to say in per second. So you can write 1 over s, you can write in per seconds. It's all the same thing. All right. What else can I define here? There's things I can define and things I can't. I can define already, even with this non-sinusoidal type pattern, as long as it's repeating, I can talk about that. Oh yeah, it's amplitude. So I could also talk about the amplitude of the wave. By that I mean the biggest excursion from 0. Right? So here's the amplitude A of the wave. Right? Now, if I drew this symmetrically, if this happens to be a symmetrical pattern, then this down here will be minus A. Right? I didn't quite draw it symmetrically though. This isn't quite as far down. So maybe it's a little ambiguous about what I mean by amplitude. I'm just going to use it here to mean the biggest excursion from 0, which happens to be amplitude is a positive quantity, but it's the biggest distance you ever get from 0. In this case, I'm going to be positive. I just define it that way. So for most of the oscillations we're going to deal with in this class, almost all of them, it's going to be a sinusoidal oscillation, and it's going to be about 0, about the oscillating so that you're about the point you're going to call we're going to talk about oscillations about an equilibrium position, and we're going to call that equilibrium position x equals 0, or whatever the vertical axis is, x or y, whatever it is, equals 0. In that case, you're going to go as far above as you get below to your maximum excursion, and you're going to say, all right, the amplitude is then either it's the height of the peak, or you can say it's the depth of the trough. Either way, it's the same number. We'll call it the amplitude. Okay, great. So we've got our Hooke's law. Now what I'm going to do is motivate where all these sine waves come from. So I've drawn a wave here that's not a sine wave, but we're going to do sine waves from now on. Why is that? Well, it's essentially because if we combine Hooke's law with Newton's second law, right? So we got Newton's second law, something that will show up probably in Thursday's midterm in some form or another. We have f sub x equals let's do it in the usual form, ma sub x. And of course, this is the net force we're talking about for Newton's second law. And it's the x component of acceleration, just to make the equation self-consistent, right? And what is acceleration? Well, we can think of it in terms of this second derivative of position, right? As you know, All right. So now we've got a relationship between the second derivative of position with respect to time and this force, and let's just substitute in our Hooke's law. So suppose you've got some situation described by Hooke's law, which is restorative force that's linear with your displacement, and let's see how we get a sine wave out of that. Or let's do it this way. Let's check to see that that's actually a valid solution, right? The way these things always work with differential equations. How many of you have had differential equations as a standalone class? How many of you've all had differential equations though? You're all used to solving differential equations from your calculus class, right? Well, there's only two differential equations that ever come up, and well, that's a lie. Many come up in physics, but there are two that come up all the time in physics classes and biology classes. One of them is the one I'm about to write, which just says that the second derivative of something equals itself with either a positive sign or a minus sign in front of some constant. And the solutions to all those things are sines and cosines. That's what they are. So let's just go ahead and check that out. If I stick in here what I have up there, I say minus k times x equals m times the second derivative. Okay, so here's the as advertised, here's my differential equation. Here's x, here's second derivative of x. There's no first derivative that appears in this equation, just second derivative. I can make this a little bit simpler maybe by putting all the constants on the same side. So I can say, all right, let's let x equal, let's see, what will it be? It'll be negative m over k. Spring constant on the bottom, mass on the top, times the second derivative of x with respect to t. So the way differential equations work at this level anyway is we have lookup tables essentially. There's only a few differential equations we can solve, and the one that always shows up is sine. So let's just substitute it in and check and see where the constant that appears in this equation appears inside my sine or cosine wave. So let's go ahead and do this. Here, why don't I do this? Why don't I make a bunch of pictures on this board of position and then velocity and then acceleration. So if I take position as a function, as a function of time, say, all right, let's assume one of those forms. Let's use cosine for the sake of argument. Doesn't really matter. So I've got some cosine. All right, and so we'll give this some amplitude a, and so that means this is minus a, right? This is my 0 point right here from the x-axis. We already know how to label these other things. You know, this is going to be t. Here, let's give myself enough room. Here's t. Okay, here's my capital T. That's the period, right? Here's t over 2, right, etc. Okay, so there's my cosine. X equals cosine of. Let's see. Well, let's give it some name. I can't put just t inside the cosine argument because t has units. So let's multiply it by something that's got units of 1 over t. That omega right there is going to be a different kind of frequency, the angular frequency. This over here was just plain old, I guess I call it linear frequency or plain old regular old unspecified frequency, right? Or I shouldn't say unspecified. I should say unqualified frequency. This is angular frequency, and I need an amplitude in the front. Let's put a in the front. So then this picture right here is of that position as a function of time. If I substitute that in there, what do I get? I need to take two derivatives. So let's take one derivative. The first derivative of cosine is what? What's the derivative of cosine? Yeah, it's a sign. Is it negative or positive sign? It's negative. And the way I keep that straight is I look at the right of 0, and I see that the slope is negative as I go to the right. See that? It's falling off. So if I now plot a picture of v as a function of time, right? Excuse me. It starts off at 0 because after all, velocity is the slope of this curve. Velocity is 0 right there, so this is the 0 point. It gets to 0 again right here. So I know it's going to go through 0 there, and it goes through 0 right there because again it's horizontal. So I get a 0 right here at the period, right? Over here I have negative value. Excuse me. Now I got to frog my throat. It goes like that. And if I did a decent job. So what's the amplitude of this wave, or what's the biggest excursion? Be careful. I'll try to use amplitude to refer to x, to the biggest excursion for x. Well, let's take our derivative. If we take a derivative of cosine, we get negative sine. But then we have to, by the chain rule, take the derivative of the argument of cosine with respect to t. Right? So I'd say, okay, v is dx dt, and that equals, let's see, I get a factor of omega that comes out. And notice the a in front stays in front, right? So that means that I get an omega, I get an a, and now I get, a minus sine of, and it's the same argument inside the sine wave as we had in the cosine before. You still have the omega t as you had before, right? So the thing is having a minus w in front, and you change cosine to sine. Great. But I need to take a second derivative now first, so let's go one more, and that gives us our acceleration, right? So what does that look like? I'm sure this is an unnecessary review for many of you, but if you'll bear with me, I'll go ahead and do one more step. It's always good to see it again, I think. All right, so then now we start off with a negative slope. So I know that the initial value is going to be its maximum negative value. What is the derivative of negative sine? It's going to the negative sign is going to remain, right? The derivative of sine is positive cosine. The derivative of negative sine is negative cosine. And again, we get a factor of the w, or it's not w. Mastering physics would scold me for that, right? It's an omega, right? So the omega comes out. So I'm going to get an omega squared in the front. Minus sign stays, and I still have the a. So I wind up with a of t is second derivative, with respect to position of time. And that becomes negative omega squared a times sine goes to cosine now. And that's why it's useful for that differential equation over there. We start out with a cosine. We end up with a cosine if we take two derivatives with a minus sign in front. And we get some constant in the front. And so now our job is to match up the constants from Newton's second law, right? With combined with Hooke's law. And the constants we get for this generic form for any sinusoidal function, or I guess, the original a cosine omega t, we can figure out how to relate all the constants. Okay, so to draw a picture of this, I see it starts off at its the biggest negative value here, and then it goes through 0 right here. Anyway, you know what it's going to be. It's going to just be a cosine wave. But it's got a minus sign in front. So it starts off like this, goes through a max over here, goes like that. It ends up right there. So there's our t. Good. And again, we need to, I didn't label my big excursions there. So over here I've got what? Omega squared a. That's how big it gets. Omega squared a. Oh, yeah, I need a minus sign here, so myself a little room. Minus omega squared a, right? Good. And then up here I should have written omega a and minus omega a. Okay, super. All right, a little trip down memory lane with all those cosine and sines. And so we plug it in here. We get that, well, let's see. X is a cos omega t, so I get this. A times cosine of omega t equals negative m over k times the acceleration. And the acceleration is negative omega squared a, right, times the same old thing, cosine of omega t. Good. So what I've done here, it's kind of funny to call it solving. What I've done is I've made an ansatz, right? It's a fancy way I say I took a guess. I took an educated guess. It's going to be a sine wave or cosine wave. So I've seen this differential equation before. And I just went ahead and calculated what those values are, what those functional forms are. I plugged it in here. You see, sure enough, on both sides of the equation, you get a cosine omega t on both sides. You can cross it out. And you get an a on both sides. So you notice that the amplitude, whatever it is, for any amplitude, it works, right? That's interesting. That means if you have a mass on a spring, no matter how far back you pull that mass on the spring, right, and let it go, the oscillation is going to wind up following the same sort of time course. You're going to get the same period out, same frequency. Kind of surprising. But anyway, that's the way it works out. So the a gets canceled on both sides, right? There's two minus signs here, so that cancels out, thank goodness. So that means it's positive on both sides of the equation. And what remains is that this over here is just 1 now, equals all this stuff. So now what I can do is solve for omega squared, right? So what does omega squared equal? Well, if I take this on the other side and multiply by k over m, I find that omega squared, right, equals k over m. Or the way we usually write it, we say, okay, omega is the square root of k over m. Kind of hard time with my chalk. There we go. So first of all, let's check our units. So what are the units of these things? Omega is, well, it better have units of 1 over time, right? Because it's being multiplied by time inside the cosines argument. So let's check and make sure that's true. Well, k is a spring constant. It relates a force to position, right? So k goes like newtons over meters. Newtons are what? Kilogram meter per second squared? So that means kilogram per second squared. All right, that's kilogram per second squared. And this thing is kilogram. So the kilograms cancel, so you just have 1 over second squared. Square of that is just 1 over seconds. Good, the units work out. This thing has units of 1 over time, right? So that's good. What about limits? Does this thing make sense? Does it make sense that the frequency should go like the square root of k over m? Well, the square root part's a little trickier to think about, but if we just concentrate on who's on top and who's on the bottom, like, k's up in the numerator here, right? So that means that I'm going to get a bigger frequency with a bigger spring constant, and that makes sense. If I have a stiffer spring, right, it's going to move that mass back faster for a fixed amount of mass. So if I put a mass on the end of it, so here's a spring now, right? I'm going to put a mass on here and let it oscillate. Oop. Oh, sorry about that. Here, let's use one that's a little bit. Gosh. So I use a bigger mass now. Will it be a less or a greater or a lesser frequency with a bigger mass? Mass is in the bottom, so bigger mass means it'll have a slower oscillator or a lower frequency. And sure enough, right, as advertised, that's good. In fact, I can get a really big mass. Here we go. This would be even slower yet, right? Slower yet. 1, 2, 3, 4, right? Almost. This is like 1 hertz, almost. Maybe a little faster, but around 1 hertz. So I go back to the small mass again. It's a lot faster, right? 1, 2, 3, 4, 5, 6, right? So that's twice as fast. So there you have it. But yeah, so that checks the mass. In terms of the stiffness of the spring, we didn't check that because this spring only has 1 spring constant k. I didn't change that. To change that, I need to have a second spring. Oh, but I may not have one. You have to take my word for it. But it makes sense, doesn't it? If I had a stiffer spring here that really produced a huge force, if I displaced it a little bit, the mass wouldn't get very far before it's turning around. As a result, it would go back and forth really quickly on a really stiff spring. Okay, makes sense. So I talked this through. I know some of you are rolling your eyes. Oh, it's how obvious, right? Clearly this is true. But it's really worth thinking this stuff through, and it's worth being reminded to do it every time because you see me make mistakes on the board. And when you're taking an exam, it's easy to get these backwards. Like right here, it's an easy algebraic error to have this one up on the side without flipping them over. But if I think through the limits, I get it right. Okay, good. And the units gets it right too. But okay, good. So one thing we noticed is that it does not depend on amplitude. Interesting, right? And, let's check that. So I just had masses on here, and I wasn't too careful about how far I pulled them from their equilibrium position. Also, you notice that I'm getting different equilibrium positions with different masses as well. We'll talk about that in a few minutes. But that does not affect the oscillation frequency. Oscillation frequency there does not depend on anything except for k and m. And by putting a bigger mass on here, it doesn't change the stiffness of the spring. If it's a true linear spring that obeys Hooke's law, doesn't matter how stretched out it is when it reaches its equilibrium position with some new mass on here, when gravity's in the problem, the vertical spring, the frequency of the oscillation doesn't depend on how far away it is from its equilibrium position as a result of some other force, like the force of gravity distorting the spring. Just k and m. So right now what I'm doing is I'm looking at the oscillation for a given amplitude. So what is the amplitude? Say, well, I have to decide what part of the mass I'm going to call. Let's do the end of the spring. So there. All right. So here's the end of the spring. All right. So there's an amplitude of, I don't know, what is it? A few centimeters, right? And we got 1, 2, 3, etc. And if I do it, let's do a smaller one, because the bigger one might fall off. If I do a smaller displacement, sure enough, 1, 2, 3, 4, it's the same. And that's very useful fact. It's going to turn out, we're going to find a similar thing for pendula, and that's really useful because a long time ago, people didn't know how to build clocks, right? They didn't know how to make something that's going to keep accurate time. When people figured this out, and Galileo figured it out actually, sitting in a cathedral, he was watching a bunch of pendula, he was watching the chandelier hit sort of an idle moment, and he was during service, and he saw a bunch of swinging chandeliers, and he realized that no matter how big their amplitudes were, they had the same period of oscillation. How did he actually measure that? So he needed a clock to do this measurement. What clock did he use when he was sitting there? Looking up, the smart guy, he sees these swinging chandeliers, some with really big oscillations and some big amplitudes, some with small amplitudes. And so he wanted to get a really accurate measure for exactly what the frequency was, or what the period was. So what clock did he use to count? Like he counted, I don't know, 10 oscillations and said, how long did that take? So what clock do you have inside your body? Yeah, your heart. As long as you're not running around, changing your heart rate. And he was just sitting there, he's bored, right? So if he's sitting there, he measured his pulse, watched the chandelier go, and realized that when he checked several different chandeliers, right, and kept notes and everything, or he's got probably good memory, just remember. He figured out that, yeah, they all had the same amplitude. Excuse me, they had different amplitude, they had the same frequency. But that's pendulum. We'll get to that in a minute. Okay, great. So this does depend on mass, and it does depend on the spring constant. Make sure I hit all the points as I move through these topics. Oh yes, mass on spring, that's right. So now we can, I should make really clear how to relate omega to f, right? So I've already talked about f in terms of some random but repeating type of a waveform. And if I look on here, I've labeled my capital T's my periods, right? And f in fact is just 1 over t. But what is omega? Well, if you think about what value omega t would have to take, so for this right here, for cosine to go through a full cycle, to start off down here, right, for negative cosine to go from down here through a full cycle back to the same thing again, that means that the argument of the cosine had to go from 0 all the way up to 2 pi, right? Because cosine of 2 pi is after you've gone through a full cycle. So you know that 2 pi, that's how 2 pi gets in the mix, because we use our definitions for cosine and sine involve 2 pi's in the arguments, right? Or how to map from the argument to what phase you're in, or I shouldn't say phase, but how far along, well, you can call phase, sure, what phase you're in of the cycle. So that means that when I get back to this point again, omega times capital T, so I stuck in capital T for little t, right?